The focus of machine learning specifically is that instead of a human adjusting the algorithm and writing a program and saying the algorithm should do this, oh, that didn't work, I'll tweak the algorithm. Instead, what you do is you program it through the data. So you'll say, look, the model works well. It doesn't work as well in this particular scenario. My solution is not to fiddle with the algorithm. My solution is to label more data in that scenario so that the model can learn from it. And it's a really big shift in mindset, particularly for people who worked with algorithms for a long time.
Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. The voice you heard right at the start of the episode, that was Dr. Michael Bewley, and he is the Senior Director of AI Systems at a company called Nearmap. And today on the podcast, we're going to be talking about aerial mapping. But this is not just a podcast episode about capturing images from planes. It's a podcast episode about what it is possible to do with those images you capture from planes, the challenges you face along the way, and what the future of this might look like. Hey Michael, welcome to the podcast. Thanks very much for joining me today, all the way from sunny Australia. Today we're going to be talking about aerial mapping. You work for a company called Nearmap, and I think now would be a great time for you to just briefly introduce yourself to the audience. So who are you? How did you get involved in aerial mapping? And after that, perhaps we can move on and talk about what Nearmap is doing, some of the processes you're involved in, and yeah, we'll just let the conversation flow from there.
Sure. I'm Mike Bewley. I'm Senior Director of AI Systems at Nearmap. Wow, that was a multi-part question. Let me try and wind back. I think what led me to Nearmap, I guess, was maybe the first bit. I mean, by background, I'm not really a geospatial person. I mean, I was one of those kids who always loved maps and things, but there's plenty of those at Nearmap. It was a really interesting set of experiences which led me into this career path. I started off actually, undergrad was engineering and physics. And then I went into an Australian technology company called Cochlear, which does medical implants. So helping the deaf to hear with electronics and software and complex audio processing. So I worked there for a while, which was fascinating, really seeing what world-leading technology looks like from the inside. Then I had always been interested in data and machine learning, and I decided it was time to go back and do a PhD. I certainly didn't want to do a highly theoretical one. I wanted to do something where I could make a difference, work on lots of data and do something practical. That led me to a really interesting place called the Australian Centre for Field Robotics, where I worked with the Autonomous Underwater Vehicle Group. And there you basically, take a robot, throw it off the back of a boat, and it will do a similar thing automatically to what aerial imagery is today. So it'll map a survey of the sea floor. And I was trying to help these poor marine scientists who were sitting there tagging thousands and thousands of images manually. I was trying to help them automate that process because it's not fun to sit there all day and work out which species of coral is in that corner of the image. There, I went into banking for a little bit, more about working with kind of big enterprise data, looking at how things work in a large organization. And then from there, I ended up at Nearmap. So it's a really interesting confluence of things where it's Nearmap is a deep technology company like Cochlear. We design and build the camera systems in-house, all the way through to the software and processing and front end work. So it's full end to end technology here. We work with a lot of enterprise customers and give them data. So it's great to have an understanding of that. And the PhD it's just so similar. It's just that was underwater and this is on land. And the scale and impact of this is just enormously larger.
So again, we're talking about aerial imagery here. We're talking about aerial mapping. And I remember the very first conversation we had, you talked about your business model. And without being too sort of sales pitchy here, could you explain the business model to us, please?
Yeah, so Nearmap was founded, maybe a dozen years ago or so. And it was really founded on a unique technology, which was a custom designed camera system that allowed planes to fly higher and faster, much higher and much faster than aerial capture normally permits. And that gave greatly increased efficiency. Now, you've got to decide what to do with that efficiency. Now, what the team back then decided was worth trying was, well, what happens if we use that increased efficiency to fly ahead of time? We'll just go and fly all the major cities in Australia and we'll do it multiple times a year. And then we'll let people sign up and they can get access to it whenever they need. And that's very different from, I guess, the standard aerial imagery model where you pay for a survey because they're so costly upfront. Whereas here you're leveraging those economies of scale and allowing all these people to access aerial imagery who'd never even considered aerial imagery before. They're doing it through a web application with some basic tools in it. And they can do things in a business sense. They can get their job done remotely in a way that they hadn't before but they're not your classic kind of GIS customer who understands map transforms and how aerial imagery is created.
Perhaps we could talk a little bit about your customer base later on, but for right now, I'd like to know more about these aerial surveys that you conduct. You talked about flying further and faster than ever before, these specialized camera systems that you have developed. Could you talk to us about that? What does further, faster, and specialized mean for you? How is it different from what other people are doing?
We've been through multiple iterations of camera systems over the last decade. And I think what we typically quote is we think we're about 4 times more efficient than current on the shelf camera systems, which is a pretty big impact when you do that at scale. And what that has allowed is that today we cover 90% of the Australian population up to 6 times a year. We're expanding our capture program in the US from 70 to 80% of the population next year, at least once a year. And we cover Canada and New Zealand as well, with really a small number of planes compared to what you'd expect.
In this case, are we talking about RGB imagery, or are we talking about LiDAR, or are we talking about different spectrums?
Yeah, absolutely. Interestingly, the very first camera systems we used were designed from off the shelf RGB cameras, but now we're much more custom than that. But it's still focused on RGB, and we have a whole suite of products relating to 3D. But that 3D is created through a technique called structure from motion, where you're looking at multiple aerial images from different angles that overlap, using pose information, and then doing some pretty complex vision work to understand, how those sit relative to each other. From that, you can create a 3D model, and then we have a digital surface model, which is kind of I guess it's a raster map. Some call it a digital elevation model. It's a raster map of heights around the place. And then more recently, we've got a digital terrain model, which is basically the same thing, except you scrape off the trees in the building.
So oftentimes when I talk to companies that are capturing large amounts of imagery like what you're doing, a big part of what they do is object detection. And I'm imagining this is what you are involved with as well. If that's the case, could you talk to us a little bit about that? What kinds of objects are you detecting based on this really high resolution aerial imagery that you are collecting?
Yeah, that's a good question. So, yes, absolutely, object detection is a thing. Now, a lot of people will run object detection kind of as needed. It's pretty difficult and expensive to do machine learning that works at scale. You can get a demo going pretty easily, and you can make something that works in a small area in a relatively straightforward way. But what we actually do is we do AI at the same scale that we do imagery. So these days, every single survey that we conduct, that's multiple surveys a day. So it's thousands of square kilometers a day. We're running our AI system to detect dozens and dozens of objects. I think we've got, in GIS terms, I think we've got about 35 feature classes that we deliver behind an API at the moment, based all on that RGB imagery, plus machine learning, plus a whole complex set of post processing.
When you think about detecting those objects and creating those feature classes, my understanding of object detection is there's a couple of different approaches to it. You could do labeling, for example, or tagging images. What approach do you use in terms of segmenting the pixels into features?
Yeah, so our system is really founded at the moment on a technique called semantic segmentation. And what that does is you take an image as input, so an RGB image, and for each pixel of RGB image, you're calculating a pixel of meaning. So for our building footprint layer, we've got 1 pixel per RGB pixel, and we're talking about 5 to 7 centimeters per pixel here. That's really, really high res aerial imagery. And when we produce a map of pixels, that basically say what's the probability that this pixel is roof, or what's the probability that this pixel is tree, or one of any other of dozens of feature classes. And then we do all the vectorization, we do post processing cleanup, we run additional machine learning models on top to produce analysis ready data products that are fit for quite a wide range of customer users.
This is probably going to sound like an incredibly naive question, but when you talk about labeling each pixel as what is the probability of it being a tree or a roof or a car or some other kind of surface, does that mean each pixel can only be one thing? Because I'm imagining a roof could be associated with a house. So if building footprints was something that you were collecting as well, do you have these kind of parent-child relationships with the pixels?
There's a problem formulation in machine learning called multi-class, and that's when you might have 10 classes, and the model will tell you which of the 10 things it is. That's not what we do. We actually do something called multi-label, where each of these output channels, and it really is a raster output channel, is totally independent from the others. If you've got trees overhanging roof, because of the way we do our human expert labeling, actually, the model tends to predict roof overlapping with, like, the roof that sticks out underneath the tree, really to a similar extent that you would guess as a human. So you get in those locations, you obviously get a pixel of we are really confident this pixel is roof, but we also are really confident that this pixel is tree.
Okay, so if I'm understanding this correctly, so each model that you run is looking for something different and it's looking at the image in isolation. So it doesn't know that you've already classified that pixel as being a house or a car or something else. Am I understanding this correctly?
Close, close. There's, I guess, with deep learning, that really is the foundation of what we do. We wouldn't be able to do it otherwise. We actually still have one global model, so that's quite a challenge in and of itself because you're trying to train one model to take in an input image and then learn things about that image that can solve multiple problems, right? So initially, it kind of learns edges and textures and things and how those compose into larger features. And at the very output of the model, you can basically have multiple outputs and you can have one output that says, switch on if you're confident that there's building, or switch on if you're confident that there's trees. So it is still one unified model, but right at the very end, it kind of shares all the information up to that point. It makes decisions on each layer independently. It's quite amazing the level of R&D that we've leveraged from the world of deep learning on imagery. So if you look at all the major companies doing deep learning on imagery, not in the geospatial space, but all the images out there on the internet. It's really a revolution that's been continually happening since about 2012. But we basically piggyback on that, and then we build our own custom deep learning model architectures. They leverage a little bit the fact that it's geospatial data. We know more about it than just random pictures of a cat on the internet because we know about the scale and we can choose our image sizes and all sorts of extra bits of information.
Yeah, and just to clarify here, you're not doing any of this based on other data sets. So this is all being derived based on the RGB images that you are capturing.
Yeah, that's right. So actually, it's fully in house. So we use our own imagery that we've processed, or that the vision team has processed and prepared. It's the same images that our customers can view. We take that as input. We've got our own custom labeling tool that is a modified version of our map browser tool. So Nearmap has this tool that I guess non-GIS experts can go and explore the world. They can look at multiple dates, multiple angles, 3D, and so on, and they can draw pictures and do projects and that kind of thing. And we have actually a whole lot of labelers who will label that imagery on specific jobs. And they'll label, are there trees in this image? Are there rusty roofs? Are there light poles? Are there power poles? Just to give you a flavor of the different sorts of things. So they label them, and that's an in-house team, an in-house tool. And then that goes into training the model, which is again something that we've designed ourselves. And then we create the output. So yeah, it's purely Nearmap data, which is a really exciting thing to kind of go all in on what Nearmap produces because it means you can optimize for it. You're not trying to make it so it will work on any aerial imagery data or satellite data or what have you. We don't really care about the quirks in other data set. We can really just optimize for every single thing we know about our own data, which is quite a lot, obviously, given we've been working with our aerial imagery for a decade or more.
But I think too, if you were to put a LiDAR on some of these planes, for example, or collect other kinds of data while you're flying over the area as well, I mean, I guess you would also know a lot about that data. Is it simply for the sake of simplicity that you just collect RGB data, or is there something else here that I'm not seeing?
So I guess the reason why we've stuck with RGB imagery in our camera systems is that that's what our customers have asked for. So this is all built on the back of a really nicely functioning business that sells access to aerial imagery for customers, so they don't have to go on site, right? They can remotely inspect and do things without turning up, which has been great in the last couple of years. So that's what's been built on, and there hasn't been need for lidar or anything else there. And then you pair that with the advent of modern machine learning, and all these other groups that have poured goodness knows how much money into researching. Your big tech companies, your big governments. Most pictures don't have depth information and lidar and things attached. So all of that research has been about how do you get the most possible information out of an RGB image. There's companies that will say humans reason about the world pretty successfully without things like lidar, that all you really have to do is we use our eyes, which are approximately RGB sensors, and we can figure out things like what object is that and how far away is it, accurately enough for me to reason about. So we do the same thing, and we find that that's enough for us to do some really powerful stuff. In our tree layer, for example, people compare it to near infrared and that kind of thing that's been traditionally used because the deep learning models derive the information from the imagery texture. and you can almost see the leaves at 5 to 7 centimeters per pixel. So yeah, I guess we're leveraging a huge amount of research and building on the back of that enables great results, fantastic results, even just from RGB.
I believe you used the word texture there. Could you just elaborate a little bit on that? What do you mean when you say texture?
Yeah, so I guess the texture of an image is in the same way that you'd have the texture of something that you touch with your hands. You might have something which is rough or smooth. When it comes to imagery, texture is more about color and the color variation. And I guess you'd call it the fine scale patterns. So we do roof material as one of our things, and whereas some people might use spectral information to tell the difference between a metal roof and a tile roof, you can see with your eyes the texture where you've got these linear features for the corrugated iron roofs. And you can see with tiles, you can see this nice texture of those neat rows of tiles. And that's even different from shingles, which we can discriminate from really quite effectively, because shingles don't have that. It's still kind of a patchwork texture, but it doesn't have that nice regularity of a tile roof. So it always comes back to, as we tell our customers who ask, if you can reliably spot it in our imagery as a human, the state of the art with deep learning, which is where we're at, is that you can do it with a model.
So you've been doing a really great job of sort of weaving in examples of these different feature classes that you're collecting. I believe at the start you said about 35 different feature classes, so different kinds of objects that you can detect based on the imagery that you're collecting at the moment. But you also said that RGB, one of the reasons why you use it is because that's what your customers were asking for. They wanted to be able to see and monitor things without actually going physically to the place. They wanted to be able to see it. So I'm curious, when you think about creating new products or so detecting new feature classes, is it a function of what people are asking for, or is it just a function of what you can do in terms of the okay, now your model is better, now we can do this, so you add those things to them. I'd be curious to know what is sort of pushing the development of new detectors, being able to create new feature classes.
Oh, look, it's very much customer driven. We've got customers in a range of industries. There's a lot in both the local government space and the insurance space, particularly that are using our AI data. So they have long, very long laundry lists of things that they'd love to see out there in the world. So we take from them and prioritize, obviously, and then we add them to the model. So what's an example? I mean, roof condition is something we added recently due to customer requests. So things like structural damage, roof staining and ponding and rusting, people really trying to work out what's happening to a roof. And we've talked a lot about RGB imagery and what you can get out of that. But we also use our 3D information, which, yes, is derived from RGB imagery. But we now do things like, count the number of stories out on a house, or measure its height, or measure the dominant roof pitch automatically. And we do that through machine learning on our 2D imagery, and then actually machine learning on our 3D mesh, different kinds of models that happen. I guess if you're a GIS person, you're probably used to running various algorithms on your software of choice. You might process with one algorithm and then the next one and the next one. We do that at massive scale, and by massive scale, we're talking. I think we're up to billions of features that we've produced on millions of square kilometers worth of 5 to 7 centimeter per pixel image. So it's the industrial scale machine learning is the real challenge. We've not really hit walls that relate to the nature of the sensor that we have, because the R&D it's so far out there, and our imagery capture program is tuned for what our customers care about. So if our customers need to be able to spot something, that's what our imagery capture program is designed for. And then because the machine learning models can basically, if you train them well enough, basically mimic a human's ability to recognize something in an image, that means we can basically achieve what we need to achieve with our models. But yeah, it's the industrial scale stuff that's really fascinating.
That is fascinating. I was going to ask you about this later on in the conversation. And the question I'm going to fire out now, and we'll see how you react. So the question was going to be, a lot of companies are constantly looking to improve, make things better, make things more efficient. And if you had the choice between two things, either improve the sensor, collect better data, or improve the model, which one would have the greatest impact? But it sounds like what you're saying is the model, is the processing at an industrial scale, which would actually have the biggest impact in terms of improving your products and services.
Yeah, I mean, our sensor system has been fine tuned over a long period of time, more than a decade. We are still improving that. So we've got another camera that is just even worlds ahead of our current best in class coming. So we don't stop on that front. We're still pedal to the metal on R&D for our sensor systems, but at the same time, our machine learning models continue to advance, adapt. So we run we run at such incredible scale that it gives us some advantages that are not possible otherwise. So, for example, if I run a survey, I can then go and find areas in that survey where, I don't know, swimming pools overlap with water. And that might be something unexpected, or a solar panel is visible on a tennis court or something. We can look for these automatically because we process these vector maps at massive scale. And then we can use that to improve the model because we can get the humans to look at that and say, is that weird because the world is a weird place? And everyone who's involved in GIS and has looked at lots of examples of the world know that there's some crazy stuff out there. So they can either validate and say, yes, that is indeed there. That's a swimming pool on a cruise liner in a water body. That was an example we saw the other day. Or they might say, no, that's actually incorrect. The model's got it wrong. So you're really lasering in on any corner case that doesn't work to label more, and that those labels feed into your system. And so, some, I guess, of your listeners might have built models themselves by hand labeling some data. The scale that we're labeling at, I can't remember how long ago it was now. A little while ago now, we cracked past the million images worth of labeled data mark. So it's pretty big scale of labeling, but you're scaling that up orders of magnitude. You might at that scale say, well, why don't you just label it all? Well, we've got tens of petabytes of imagery already, and we're increasing our capture programs. So you need these models to automatically scale that up.
Okay, so it sounds like we've moved on, and we're talking almost a little bit about ground truthing now. Where you're looking for problem areas, edge cases. So you're creating these vectors based on the objects that you're collecting, and say, well, can the solar panel exist in a tennis court? I think was the example that you gave. And if you ran into a situation where that was the case, then you would have a human look at it. So this makes perfect sense to me. Then you begin to adapt the model. Does this make sense? Okay, yes, it does. Add it to the model as a labeled image, as something that the model should be looking at in the future. What about change detection though? Because if you're constantly changing the model, constantly updating the model, when I look at change over time, how do I know that I'm actually seeing change in the environment over time, or just changes that you have made to your model?
That's a great question. That's a really good question. So change detection is, I've heard it actually a few of the podcasts that come up on your show. People talk about change detection as this great unsolved and challenging problem, and it's really tough, and that's basically because any difference between, like if you're doing change between two different dates and you're trying to understand what the differences are, you've got both the errors and the meaningful change, and so the meaningful change is the signal, and the errors are the noise, and quite often the signal you're looking for is maybe even lower than the noise unless you have really impeccable quality. So we have firstly focused on incredibly high degree of accuracy with our models. So you get results that you just can't get by hand labeling stuff yourself when you're more than a million images worth of labeled data. Now, if you're looking for whether there's been a change in the model and you want to do change detection, we can just run our model on old data. So any of our historical surveys over the past 10 years, to an extent, just snap our fingers and run our latest machine learning model on it. And we've got quite a sophisticated versioning system for our models. So I think we're up to Gen 4 Lightning Bolt 1.1 now as our latest version. So our customers can really see the provenance of where that data has come from. It's not just random changes and fixing things. We've had to build in quite a lot of maturity that I guess I certainly didn't appreciate at the very start of this journey 4 or 5 years ago. But now, yeah, you've got these nuanced versions in the data. You can run change detection. You might want to match. People are often matching season for season, so you might want to go leaf off to leaf off or leaf on to leaf on, depending on your preference, one year to the next. But we've had people calculate changes in percentage tree cover over 10 years. So that's how I want to give me data at 2020 and go back in time. And can you give me the 2010 data as well? And because we're just running it on our imagery, we've been capturing consistently since then, we can do that. And then at the moment, actually, we've got our more advanced customers calculating changes themselves.
Does this all mean that you have to be relatively precise, or relatively consistent, I should say, in terms of when those surveys happen? I think you talked about leaf on, leaf off. So we're talking about capturing images of the surface where they're not covered by vegetation and where they are covered by vegetation. What does that like preferential window of time look like? Are we talking each survey is captured within 2 weeks of a specific time period, or 3 weeks, 4 weeks, 5 weeks?
That's a really good question. I would defer to the knowledge of our learned survey operations team. These guys are absolutely ninjas when it comes to understanding weather and seasons and logistics, because they're basically having to ship these cameras and planes all around the country to chase the right weather, the right season, So it's quite different from something like satellite data, which is it's happening regularly, but you might get clouds, you might, get the wrong season, and the person at the end of doing the analysis has to work out what the right stuff is. Whereas I've been amazed at how few clouds there are in our imagery. I thought that was going to be a huge problem when I turned up, but they just don't fly the planes if it's too cloudy, unless they really have to. They're trying to choose the optimal lighting conditions to fly. And then in the US, for example, they're chasing the leaf front as the last of the snows melt, and just before those first buds appear on the trees, they've got this fleet of planes that's chasing that across the country.
It's absolutely amazing, I have to say. I was during a pre-interview conversation, I was completely blown away by some of the work that you're doing. So you mentioned this 35 feature classes that you can currently detect and segment. I'm assuming there's a lot more objects out there that you'd really like to be able to detect and segment. Can you give us an understanding of where this is going, what the future of these feature classes might look like?
Yeah, absolutely. I think where the modern deep learning revolution began was with this competition called ImageNet, and that's one model which produces 1,000 different outputs. Right, it recognizes 1,000 different things. So that's my sort of benchmark in the back of my head of where I want to go with this. And the really interesting challenge there is how do you scale up the definitions? Right. So on the one hand, you can label swimming pools, and it should be obvious what a swimming pool is. Except you've got to think about questions like: do you include above ground and below ground swimming pools? What if the swimming pool is empty or half under construction? What if the swimming pool's covered? What if it's like a jacuzzi or a hot tub or one of those temporary paddling pools or maybe a garden pond? And if you do this right, the machine learning models can actually learn all those nuances. But they can only do that if the humans are consistent with all those nuances. So we've actually just hired what we call an AI ontologist. Her full time role is coming up with new definitions and thinking about how they relate to each other and the existing ones. So if you want to know what a swimming pool is, go to our website on docs.nearmap.com, and you can see our definitions there. And it's what does it include, what does it exclude, and we've got, I guess, for our labeling team, we've got a multi-page training manual for how you label each feature class, and it gets really nitty gritty and complex. And another good example might be if you're labeling roofs, is a caravan a roof like a mobile home? Maybe not if it's on the road. What if it's permanently parked in a location? There's just so many fascinating corner cases that come up in the real world. So you've got to have a way of scaling the way you deal with those if you really want to get great results.
This might sound like a really naive question, but is there any sort of standard definition of a swimming pool? Are there commonly understood definitions for these things out there in the world, an ontology that we could borrow from and say, okay, well, this is how the internet understands a swimming pool, for example, and sort of build on top of that, or at least have something that you can relate back to? Or do you need to create these definitions from the ground up as you see them?
We'd love the former to be true. And there are actually lots of ontologies out there, but they're rarely specified to the depth that's necessary. So what we actually do is we interview our customers, we talk to them, and they'll tell us, we want swimming pools, and we say, well, what do you mean by that, and how are you going to use it? And it's really the question is how you're going to use it is what drives the way we define it. But we find that we can get a lot of commonality between different use cases. But then sometimes there's another use case, and we'll just have to create another slightly different feature class to match that use case. So it's a fascinatingly nuanced problem that few have the patience for, but personally, I love it.
So, using this approach, if we had endless time and endless resources, would we ever run out of things that we could define and capture?
I don't think so because we keep inventing new physical things. And really, our mission in my particular team is we're trying to create this rich and accurate semantic picture of the world that represents what's there and that can be used for many different things. And there's just so many objects, and people keep inventing new architectures. Solar panels are changing, solar hot water systems, there's new types coming out. There's just so much new stuff and so much nuance. You have to decide, does it semantically match the existing definition and should it be added to that, or does it break that semantic link and it has to be a new thing in its own right? And both things can occur.
Do you see anything? Is anybody doing any work on some kind of standardization of this? Imagine the potential if these kinds of definitions were interoperable. If I could take a swimming pool from you or a swimming pool from someone else and know that, okay, well, these things are the same.
Yeah, I guess that's one type of, I guess, interoperability you could get. What I'm hoping to achieve is that because all of our products for all of our different customer segments are derived from that same source of truth, right? We've got one definition for tree canopy that we've got local governments using, we've got insurers using, and it's the same model in Australia, the US, New Zealand, and Canada. And if you have all these different people involved in, urban planning and organizing your local government and construction and environmental groups and researchers and all these people are actually referring to that same source of truth, it could save so many problems. But I guess to solve these problems, you have to do them at scale. And there's not really anyone else doing it at this sort of scale at multiple points in time on hundreds and hundreds of cities.
Early on in the conversation, you talked about, I think it was rust detection or damage detection on roofs. Is this a feature class for itself, or is this, do you look at the feature classes that you are creating and then say, okay, we're based on this knowledge, where these things overlap, that's where we have damage on the roofs?
So the roof condition. So we bundle up our feature classes into packs, basically AI packs, and the roof condition one at the moment is 5 different feature classes. Let me see if I can remember them. We've got ponding, we've got rusting, we've got temporary repair, we've got structural damage, and we've got staining. So discoloration or staining on shingle and tile. So if you pull from our API, so we've got an API that allows you to send in a polygon and you get back up to a square kilometer at a time of this vector map that's been pre-computed. What you get back in that payload is you'll get a roof as a polygon. It'll have attributes that tell you what percentage of that roof is covered by each of these things. So, the roof is 10% structural damage, 20% ponding, and maybe there's 10% rusting because there's a little metal extension. It'll tell you how many square meters of each. And then you also even get the features themselves of these. So you see where the little blobs of rusting are, or if it's tree overhang, you see, is this one large section of tree overhang on the roof, or is it little tiny blobs all around the edges? And I think the interesting thing for a lot of our enterprise customers is that allows them to craft whatever data they want straight from the vector map, and they turn that into columns in a spreadsheet. And it's just so powerful when you go from that vector map as you wish for your particular use case, and then you turn that into spreadsheet, which maybe you feed into a machine learning model to estimate risk or something like that.
I couldn't help but think when you're talking about the really powerful thing here is that I can take that and turn it into a spreadsheet. Because for years we've been fighting the other way, right, in the geospatial world. Make your data visible. The magic here is that we can make it visible and we can layer it and we can align it based on its spatial relationships and do some analysis on it. And it's interesting to hear that you say the magic is that we go back the other way.
That's the magic for customers. The magic for us is actually around alignment, and I'm glad you mentioned that because I was wanting to talk about that a little because I know geospatial data sets are often interesting in terms of alignment, trying to pick things on the same date or that have been done with the same map projection or whatever. So if you think about what we've got these aerial imagery surveys which are really really quite accurate in terms of position on the ground, and the AI lines up perfectly with them because it is produced by them. So if you want to plop your little roof outline on top of your imagery, you see it perfectly aligned, or your trees, they just line up perfectly because it's the same date and it's the same pixels. And then all these different feature classes line up with each other because you're not trying to merge multiple data sets. And then that's done in a consistent way across, gosh, it's hundreds and hundreds of cities in the US, for example, and captured multiple times a year, just this with this consistent format.
Are you seeing the same kind of consistent and accurate alignment between surveys as well?
Yeah, the again, the vision team works pretty hard at that. They use ground control points in various situations. The camera systems are actually really, really good. I can't remember the specs to hand, but the pixels are 5 to 7 centimeters per pixel, and I think it's some tens of centimeters in terms of how much shift there is. So there'll be a little shift, but not a lot because they can, when they process the next server, they can look at the server they've already done and make sure there's a level of alignment. That's really a lot what we play on. It's that we don't do these sort of bespoke things which stand separately but are designed to be used separately. We capture very consistently, and then you make that available to customers. So local government, you've got people looking at trees and trying to understand how the built environment interacts with the natural one, looking at heat islands. You've got them trying to figure out which areas have changed so they can see, update their records for land tax and all that sort of stuff. And that exact same vector map that sits under the hood is being used by, insurance to look at the trees for bushfire risk, or it's being used by researchers to understand better how we can quantify what happens around heat islands, for example.
So you mentioned heat islands a couple of times there. Now, at least in my understanding, this is not an object we can segment and capture as such. It seems to me that it's more a function of the materials that are used in different objects. Does this mean that you can segment materials that objects are made out of?
We can segment materials insofar as you can observe them as a human on the imagery. So we do tiles versus shingles versus metal for roof types. And we do concrete and asphalt and lawn grass. So, impervious surface modeling, which people use for stormwater runoff and things like that. We do quite a lot with materials. Obviously, there's a limit, but that limit is really the same as what your limit is with your eyes. So I think you've got a lot of local governments who are trying to move from these hand digitized maps that are really brilliantly accurate, but as a result, their hard work and they get very out of date. They're trying to keep up to date and they're trying to compare what's happening in their area over time and at scale. And the only way they can do that is with automation.
Yeah, so let's talk about automation. Let's talk about AI for a little bit. This is a huge part of what you are doing. You are not the only company doing this, the only organization interested in using AI in this way. And I think years ago, we often heard people talking about big data. And now we just talk about, we just talk about data essentially. There's still lots of data around and it's getting bigger, but now we just take it for granted. It's data. Yeah, you have a lot of data. We all have a lot of data. Do you think we're going to reach the same point with AI, with deep learning? With these kinds of models that you're developing, where we don't talk about them as being AI as such. We just talk about them as part of data analysis. Yeah, we're doing data analysis. And of course, we're using AI.
Perhaps. I guess for an end user, it doesn't really matter, or it shouldn't matter, that it was produced by AI or drawn by hand. For our customers, they just want a vector map of their area. However that comes, what they want to know is it fit for purpose? So with automation, we have to reach that level that it's fit for purpose, and they get some advantages. Things like, because our output system is fully automated, we don't hand touch up any of our output results. And what that means is you can get the data really quite fast. And yeah, look, I mean, we do work with pretty large data. I mean, as a company with tens of petabytes of imagery, there's some quite interesting scale problems that we have here that you don't often get. It's about a lot more than scale. It's about the nuances of getting the system right, which is why my area is called AI systems. It's not just about, can I train a machine learning model? It's about, how do I get really clean labeled data, and how do I feed that to a model and train that reliably and robustly? And how do I evaluate that model? How do I run that model at scale? And how do I improve it? How do I do all that with lots of feedback loops? And there's really quite a lot of complexity in how the different parts interact with each other. And that's really where the challenge is.
So I think people like us are interested in exactly those problems that you're describing there. I find it fascinating. How do we do this at scale? How do we do this consistently? How do we make this better over time? I think it's a really, really complex problem to solve. And again, I find it fascinating. Is AI, is machine learning, are these models, are they ever part of your promotion? Like, do you need to use those words to help your customers understand that, hey, this is amazing what we're doing here. This is reliable. Do you use those words, or do you use some other kinds of words that makes it easier for them to understand? I guess what I'm getting at here is I'm trying to understand the connection between all this magic and what your customers actually want, what the people that are buying this actually want, what the market says or wants.
I mean, the product is called Nearmap AI, and so we do use that term. But we also talk about rich HD vector maps, and we talk about what the data is and what the customer can get out of it, because that's what matters to them. It does make a difference that it's AI generated, because it may alter their expectations of where the data comes from. A lot of it is things which they're not used to being possible, like having an automatic flag of how many stories a building is on every single building in your local government area, and being able to get that on any date you want. If you've got in your head that this is being done by humans, you say that that's silly. That's, can't reasonably do that at scale, and I wouldn't be able to order a historical date, because that's a luxury that is we can't afford. Whereas with automation, we can run at scale. So it has some different properties, which is why it's useful to talk about that a little bit. And I guess it's exciting. I mean, everyone loves to talk about AI and think about the possibilities that it's opening up, and it certainly is opening up new possibilities for our customers. So I think it's reasonable to use the term.
Do you think people have a good understanding of the limitations of AI and the possibilities of it?
Probably not on the whole. I mean, no one does, because this is still it's a fairly nascent field that is developing. But we sometimes find customers asking, "Well, how accurate is it? Can you give me a number?" And that's really hard to do correctly and without context. So what we prefer to do is to say, "Why don't you take a look? Here's a sample from your area in the context that matters for you, and you can see if it's fit for purpose." And that's really what matters at the end of the day. They don't Doesn't really matter what the numerical accuracy is. What matters to them is that it works in their particular local government area, for example, that it detects trees as well as they want it to detect. Yeah, it's really usage and use case focused. We try to steer people away from thinking about, well, what model architecture do you use, or what are your performance numbers, because those are less relevant than what does the data look like in your area. Here, have a look. So we allow people to visualize it and explore it in the map browser tool. And that visualization, the primary purpose of that it serves, is to help them understand how this works. What kinds of things might get missed? Like if you've got a swimming pool, we've just got a little corner of blue sticking out from under trees. We'll often get that because the models work really well, but we might miss it, or we might get it with a lower confidence score. And customers can see that when they visualize it, and they sort of build an intuition for how the AI system works, and then that allows them to make use of the data.
I think that is so smart because it kind of reminds me of what Google Maps did for us all. It put us at the center of the map and showed us things that were relevant to us, things that we could understand and relate to. And it sounds like that's what you're doing in terms of showing people, okay, this is what it can do and this is what it can't do. This is where it's going to work and this is where it's going to have some other problems. Here, it's relevant for you. You can relate to it. Take a look. I think that's a really clever approach. I want to stay with this sort of theme of understanding AI just for a second here. If you could explain one thing to people about AI, what would it be? What's the one thing that you find yourself explaining all the time or trying to help people navigate?
If I think about AI more generally, particularly if I'm explaining it to people who work with algorithms, GIS algorithms or anything else, the focus of machine learning specifically is that instead of a human adjusting the algorithm and writing a program and saying the algorithm should do this, oh, that didn't work, I'll tweak the algorithm. Instead, what you do is you program it through the data. So you'll say, look, the model works well. It doesn't work as well in this particular scenario. My solution is not to fiddle with the algorithm. My solution is to label more data in that scenario so that the model can learn from it. And it's a really big shift in mindset, particularly for people who worked with algorithms for a long time. But it turns out, based on, if you look at what the tech companies have done, data at massive scale with machine learning always beats a hand rolled algorithm. As long as you can get good, clean data, clean labeled data is the absolute key. And then you can train a model and run that at scale.
I really want to thank you for your time. I've really enjoyed this conversation. It's been more sort of businessy than what the typical podcast episode is, but I think this is a really important thing to understand. A lot of us are trying to build businesses or involved in businesses, and I think you've been really open and honest about talking us through what the business of Nearmap looks like, who the customers are, the relationship between Nearmap and the customers, why you're doing the things that you're doing, and I really appreciate that, as well as all the technical understanding that you've given us about your process and what it means to be collecting really high resolution aerial imagery and then the products that you can build off the back of that. Really appreciate it. Thank you so much. Is there anywhere the listeners can go if they want to reach out to you, see some of the work that you're doing, or ask questions?
Yeah, so I guess for Nearmap as a company, we're available on all the social media platforms, things like LinkedIn, Facebook, and Instagram. And you can also register for a free demo of this stuff and ask for demonstration at our website, nearmap.com, nearmap.com. And if you want to actually see for yourself, there's some great material there. If you want to get in touch with me personally, usually LinkedIn is the better choice. You can search for me there. I do have a Twitter account. If that's your thing, you can jump on there. But yeah, love to connect and catch up, because I'm at the point where we've built this stuff. We know it can do amazing things, and we just really want to make connections with people who want to do those amazing things.
I'll have to get those links off you, and I will put them in the show notes so the listeners can click through from there if they're interested. Thanks again, Michael. I've really enjoyed talking with you. Cheers.
Pleasure. It's been fascinating.
So I really hope you enjoyed that conversation with Dr. Michael Bewley, the Senior Director, AI Systems at Nearmap. And I really hope, if you're interested, I hope that you reach out to him. I hope that you connect with him. But I understand it's difficult to reach out to people we haven't met yet on the internet and introduce yourself. So if you're looking for a conversation starter, you could say something like, "Hey, Michael, I heard you on the Mapscaping podcast, and I'd love to connect with you here." If you're looking for something else, maybe another way in, another angle to approach this, try asking a question. Say something like, "Hey, Michael, why is it that your title is Senior Director, AI Systems?" I'm sure either of those two approaches will lead to some really interesting conversations. So there were a lot of great takeaways from this episode, but the thing that really stuck out for me was something that Michael said right towards the end of our conversation. And it was the idea that you program an algorithm with the data. So if something goes wrong, we don't go in and tweak the algorithm itself. We get more data. We show it more of the kinds of things that we want it to be able to find. But this idea of programming it with the data, I think that was, for me anyway, there was a fundamental shift to how I think about artificial intelligence. And I think it was just a really elegant way of saying it. So I want to play that clip for you again here, just in case you missed it.
If I think about AI more generally, particularly if I'm explaining it to people who work with algorithms, GIS algorithms or anything else, the focus of machine learning specifically is that instead of a human adjusting the algorithm and writing a program and saying the algorithm should do this, oh, that didn't work, I'll tweak the algorithm. Instead, what you do is you program it through the data. So you'll say, look, the model works well. It doesn't work as well in this particular scenario. My solution is not to fiddle with the algorithm. My solution is to label more data in that scenario so that the model can learn from it.
And that's it for another episode of the Mapscaping podcast. Thank you so much for tuning in all the way to the end. It's really, really appreciated. As always, you're more than welcome to reach out to me on social media. You can find me on Twitter at Mapscaping, or there'll be a link in the show notes of this podcast episode to where you can catch up with me on LinkedIn. I would love to connect with you on either of those two platforms. And that's it from me. We'll talk again next week. Bye.